In this video, we are going to look at max power transfer theorem, which is the last theorem in chapter 9 we are going to take a look at. So let's go ahead and look at a definition. So what I've got drawn here is max power transfer theorem, and it says to maximize the power delivered to the load, set RL to RTH to RTN. So we know from our Thevenin discussion that we come up with a circuit like this when we want to change out different loads and see how they perform. So if we already have the circuit in this configuration, if we want the maximum power transfer, then RL has to equal RTH, right? So when again, when I say RTH, I'm also talking about RN. The Norton resistance and the Thevenin resistance are identical to one another. So same thing if you have the Norton equivalent here. RL equals RN, okay? And that's going to give you the maximum power. So if we talk about, well, what if you add more resistance or less resistance than that? If we add less resistance, we could take it all the way down to a short. So what would happen to the voltage drop across here? It would be 0 volts, right? Because it would be a short. But you'd get the maximum current. So obviously, if you want to have a bigger current, then you would use a smaller load resistance value, okay? But if you take it all the way down to a short, then you can get the maximum current through that those two terminals that you can, okay? Now, if you go the other way and add resistance all the way up to infinite resistance to create an open circuit, well, then you get Vmax. And that takes us back to the discussion about having a break in the circuit and having the full voltage of the source across the break. When we talked about, potentially looking to see if your Christmas lights are good or not. Okay, so if you could measure the voltage drop across each light, you would know which one is bad if they were plugged in, because you would see the full voltage of the source that's driving them. Okay, so same thing, we use Norton and Thevenin's chapter 9 techniques and get it down to this condition right here. And then if we wanted to say, okay, where's the maximum power transferred at? Well, we already know the answer, okay? Here's the other thing that I want you to know about when we're in this position, when we are at max power transfer, okay? Efficiency, and this is something that's really good for your appliances in your home, because if they have a high efficiency, that means they're using, power out over power in times 100%, right? So if you're 100% efficient, that means that you're using every bit of the power in to do something on the output. Okay, the problem is I don't think anything's 100% efficient, right? If you can get like 90% efficient, that's pretty good. So when you buy your appliance or your it's for everything. It's for your dryer and for your furnace, and for everything that you buy has that energy guide on the side of it, and it'll actually tell you what kind of efficiency it has, right? So the more that you lose in doing whatever you're doing, turning on a heater, or turning on a motor, whatever, you get less efficient, okay? If all you're concerned about is maximum power transfer, then the efficiency is 50%, always, okay? Because half the volt, like in this case right here, this is the easiest way to see it. If I were to connect this up, if these two are identical to each other, the voltage division equation for each one is going to be identical. It's going to be VTH times RTH over 2RH, right? Which is just reduces down to a half. And then it's also going to be VTH times RL, which is the same thing as this, over 2RH, which will give you a half as well. So you're going to get half the voltage here, half the voltage here. So that means that you're only going to be 50% efficient, because the total is going to be double what you get out. Okay, so it's only 50% efficient. If you want 100% efficiency, if you want all the voltage transferred, or all the power transfer, it's going to be in one of these two cases, okay? And if you want 0 or 100%, okay? So we are going to just look at the case of this right here. So I'm going to go ahead and do a problem. And I'll just do a simple chapter 7 problem that we're familiar with. Okay. And I mean, we'll just call this the load. Okay. So I want to get a Thevenin equivalent circuit here. So I'm going to go ahead and find my RTH first. Put a spot for it over here. RTH. So this one, short out the source. So we've got, you can see the 400 is in parallel with the 200 over here. 350 is in series with the meter. So there I'm showing that this has been shorted. I open this up, put an ohm meter in its place. So that's going to equal 350 ohms plus these two in parallel. So it's going to be 350. Let's do this calculation first. So 1 divided by 200 plus 1 divided by 400. Take the whole thing to the -1. I get 133. So 350 plus 133. Okay, which gives us 483 ohms. That is our RTH. So 483 ohms. All right. Now we want to find VTH. Okay, so I go back to my original problem. Now remember, when you put the voltmeter in here like this, again, it's like adding a 10 mega ohm or a very high resistor in series here. And so this has no effect on this measurement here, okay? So essentially, we just have a 2 resistor series circuit. And so we can say the voltage on the 400, which is the same as the Thevenin voltage, right? Because that's between A and B here. So that's 10. I'm not even going to bother with that voltage drop. I just want this one. 10 times 400 over 600. Again, this has nothing to do with it. This is a hanging resistor. That's what we call those. So basically 2/3 of 10 volts, which is 6.67 volts. Okay. So now I've got my Thevenin equivalent circuit. And if max power transfer is desired, then we are going to set RL equal to 483 ohms. Okay? And that makes the analysis pretty simple. So the voltage on the load is basically half of this. So you've got 3.3, what is that, 8? Call it 3.39 volts. And then the current through the load is going to be 3.3, or I guess we could do 6.67 volts. We're working with rounded numbers, so it doesn't really matter. 6, and so 966. Whoops, 6.67 divided by 966. And I get 6.90 milliamps. That gives me a power 6.90 milliamps times 3.39 volts. So the power of this load got milliamps times volts, and that gives me, well, that is going to give me 23.4 milliwatts because of the milliamps times the volts. Okay? Now, we can look and see if we would have had a short here. Okay, that's going to give us the maximum current. This is inherent to the circuit, this 483 ohms. That's the rest of the circuit. So that's going to be inherent to it no matter what. Even if we put a short in the load's place, we would get the maximum current. And if we opened it, we would get 6.67 volts across it. And that would be the maximum voltage that we could get. Okay? So this is the maximum power. It's a combination of the two. All right, so let's consult Multisim and play with this for a minute. All right, as you can see, I've got the original circuit right here, and I've got the 483 put in there for the maximum power. I also have the Thevenin equivalent circuit here that's got the RL load that we had, or that we calculated. So this should produce the maximum power, right? And so just over here to the side, I also have the VTH measurement, which you can also do, right? If you wanted to double check your VTH calculation, you can always just measure it on here. So I've got that one set up, and then I've got the voltage source shorted, and then I've got this in ohm meter mode, and so it's going to measure RTH. So here's my RTH and my VTH measurements right here, just like we would analyze these circuits on paper, right? So here we go. I'm going to simulate. Looks like we got it right. 6.67 volts, 483 ohms. Okay, so that's a good circuit. We know that. So now what we should see is that this power consumption should be identical to this one. And the easiest way to do that, especially in this newer version of Multisim, is to come up and grab a power and stick it right on the component, the watt meter. Put it right on it. There you go. Now we're measuring 23 milliwatts for each one. Okay? So here's what I'm going to do. I'm going to stop this, and I'm going to move these out of the way. And I'm going to show you what happens when we drop this. Okay? So I'm going to go ahead and change this down to 200 ohms. Okay? So this gets us close to that situation I talked about where we get towards a short, right? Because we want to make the current increase. But let's see what happens to the power consumption when you do that. Okay, so again, 23 was the max. Now we've got a much bigger current in this case. You know, if we were to measure the current here, that one is 6.9. This one is 9.77. So it's quite a bit more. But we are just not getting this, the same amount of power delivered. Let's see what happens on the other side of this. Let's try to make it a higher voltage transfer, and so make this 600. Okay, put this back on. Okay, now it's getting closer, right? 22.8, but this one is still higher. Okay, so it looks like everything matches up, and the currents matched up and everything. So again, it's only 50% efficient because half the voltage is being chewed up here and half of it's being chewed up here, right? If we go back to the 483. So half of it's being chewed up here and half of it's being chewed up here, which means that the total power that this is producing, half of it is dissipated in this resistor and half of it is dissipated in this resistor. So the power out over power in gives you a 1-to-2 ratio, which gives you a 50% efficiency. So it's not... You know, you always want to try to reduce current if you want to get more efficient, because a super efficient circuit is one that's got an open circuit, right? It's got no current pulling out of it. So the power out equals the power in because there is no power. So anyway, yep, I think this concludes this session on max power. And so there will be a couple of questions like this on the exam.